where did we stop last Thursday? And we stopped last Thursday on the at this sample problem 8.5, 8.5, and on page 455. Now, and so, and we have a wedge. We have a wedge here. We have a block B here with let's say the weight is 400 Newton, and we want to have force P here to lift it. Okay, so the biggest point is how to draw the free body diagrams. So these two are given. These two are given in the problem, and for and afterwards we get we draw these forces. Remember, in this case we don't know the reaction force. We don't know the reaction force, and we don't know the friction force either. So but we know it's because it is motion impending. So we know the ratio between M3 and F3. Okay, we know the ratio between F3 and M3. So we draw a single reaction force R3 with this angle phi s. Is that okay? Now, and I think for the book, in the book, I have mixed up R1 and R2. I think it is better to me to use the numbers, use the symbol in the book. So, and can you help me writing this? This one is R1, and this one is R2. And of course, these are N2, F2, N2, and M1 and M1. Okay. Let me put the highlighter here. So, and we don't know. I'll just explain this one. Remember to have the correct direction for the friction force, because our external force P is to the left, so the friction force is to the right. Okay. Because there are two ways to draw R3. We have R3 here, or we have R3 here. We don't use this one because P is in this. P is to the left, so F is to the right. And for this, the same is for R1. So we don't know M1 and we don't know F1, but we know the ratio between the two. We assume it is motion impending. Therefore, F1 is equal to mu s times M1. So the resultant force of M1 and F1 is R1 here, and it has the degree. It has the angle of 19.3 degrees, which is phi s to the surface normal. Okay, and for the last one, remember that that angle is related to surface normal, not to here, because this one is this angle is 8 degrees. So now, and for the last one, for the last surface, because this surface is in contact, it has a mu s of 0.35. So we have another pair of reaction force and friction force. So we have this R2 here. For those who just come in, please. I wrote this one as R2 and this one is R1, but I want to use the same symbol as the book, so I am writing it in this way now. Therefore, it's okay. So for these two, and one of our friends asked me that about this. Where is the surface normal of this surface? The surface normal. Remember, this surface normal is because the surface is vertical, so the surface normal is horizontal. So therefore, that this 19.3 degrees is here. The biggest, the difficult ones are these two, because these are not horizontal, these are not vertical, and so the phi s should be written with respect or related to surface normal here. Same as this one. Now, and we go to the, if you are okay, that we go to the calculations, and what we need to do is simply draw, because there are only three forces acting on one block, and there are also three forces acting on one block. So what we need to do is simply drawing the force triangles for these two blocks. And this one is this one is R2, and this is R1, and this one is 8 plus 8 degrees plus 19.3 degrees, and this one is 19.3 degrees. I think this should be okay. And for block A, and we have what do we have here? We have P here, and then we have R1 and R2 here. And these two angles are 19.3 degrees, and this one is okay. Because this we assume all this this does not rotate, so these three forces and they simply act on the same point, and we have because of course these two are summation f equal to 0, and of course you can write this. And we have these two force triangles. And for detailed calculations, you can read the book or the figure I gave you this morning. Oh, right, figure. This one, right? Yeah, thank you. It's okay. And after these calculations, I assume you know how to calculate the R1, R2, and R3 and P. So the result of P is equal to 423 Newton to the left. So the question I want to ask is the weight of the block is 400 newtons, right? The weight of the block is 400 newtons, and we say we need 423 newtons to the left to push it to raise the block. Why don't we just add 400 newton upward force to block B, but we do it like this? Is it logical? You get my question? And because the block B is 400 newtons, right? 400 newtons. Say the weight is 400 newtons. We can simply act a 401 newton force upwards, and then the block can go up, right? Why do we? Is it okay, or is it clever to put 423 newtons to the left in order to 423 newtons to the left in order to raise the block? Let's have let's take a look. And let's say if another case is we are not talking about the problem does not consider this, right? B is like 400 newton, and then we add the 401 newton. Say like what happens if this if I suddenly release my hand? For example, if I add 401 newton and then it goes up, and then what happens if I release my hand? It will go down, right? If I add 400 newton to the 401 newton upwards, so it will go up, and then if I release my hand, then it will go down. And for this 423 newtons, it is different. If I add 423 newtons or 424 newtons to the left, it will go up. And after, when I remove the force, the block will stay. It's okay. And so these are two different things. Okay.